For week 10, we begin the very important subject of island biogeography. You see there the references to chapters 13 and 14 in the textbook, especially chapter 13. So let's consider islands themselves. Just by their nature, they are well defined geographically. They contain very simple, easily digestible ecosystems for us to understand, and they have a long history of being studied in our discipline. So there are three general patterns that we can talk about for islands. You need to know these big three. The first one's pretty simple. It simply is that there is a species-area relationship. And this is pretty important. There are some people that claim that this pattern, this ecologic biogeographic pattern, actually predates Humboldt's latitudinal diversity gradient pattern as being the first ecologic pattern noted. But regardless, it's true for us that the species richness, the number of species that exist on an island, is positively correlated with the geographic area of the island. What that means is as the islands are bigger and bigger, they hold more and more species. And this works no matter what you're looking at. You can look at any group on land and freshwater on the island and the ocean creatures around the island, any ecosystem, anything, it happens. It's not a linear feature, even though it's shown right there. But let's get back to that in just a second. There is this very important equation, the species area equation. Both of these are plotted on a log scale. I'll put that up in a minute here, but C and Z are the constants and A is the area. So just think about that. If C and Z are anything multiplied by the area, they are going to increase the number of species there. It's plotted on log, just by definition, by convention. And what it does, it takes the function that typically has this sort of curvature, this curved, rarefied is what we call it, look. If you log both the x and the y axis, you get a straight line. And straight lines are easier to deal with mathematically. It also makes it such that c, that first constant, is where that line intercepts the x-axis. Why does this work? Because the way that animals, plants are distributed on planet Earth, there are many species that are just moderately abundant. They exist in big enough numbers, we notice them. They are the things that are common. There are very few species that are rare, and there are very few species that are super abundant. Check this out by looking at the axes. This is number of species here for the y, and then the number of individuals per species. So for instance, this one, there are just a few species where we only have collected 2 individuals of it. Look over here. There are even fewer species. Let's say there's 5 species where we've collected at least 3,000 or so species, but there are 35 species where we have collected the sweet spot in the middle. Taking this function, which really sort of approximates a normal function, and logging both sides gives you the straight line distribution that we use for plotting. If you look at this, if we look at any given island, and here's an island in the South Pacific, Kwajalein, an atoll, a coral atoll, that if you sort of count the number of species here, this would have a certain number. Take exactly the same area on the mainland, or cut out this small area on a larger island, and both of those would have more species than this one. The second pattern that we need to consider is less universal, but still important nonetheless, and that is the species isolation relationship. Namely, if you imagine a large mainland, a continent, and then islands sort of separated from it by progressively larger and larger distances, the islands that are closest to the mainland will have the highest diversity, and then that diversity will decline in S, richness, as you go away from that mainland. In the graph here, the x-axis is distance from New Guinea, which is it is an island, but we're considering it our mainland because it's a very large island. And degree of saturation, that's a different measure than actual richness, but it's a proxy in this case for a number of species. And notice again, the farther you are away from New Guinea, the less species there are. This is typically plotted as a semi-log distribution, where the species richness, S, the y-axis, is logged, but the island isolation, which is just a distance measure, is not, and that results in typically this negative slope diagram. This is never as clear as the beautiful species area relationship, mostly because this isolation is never just a straight linear feature. If you consider here the mainland of Australia, and then all these different little island nations and island groups out here, well, Pitcairn, which is a straight linear feature east from Australia, has a certain distance, certain isolation, but then how does that compare to the Northern Mariana Islands, which are not in the same linear direction, the Marshalls, the Solomons, etc.? So if the model were exactly as, or if nature were exactly as the model, with a mainland and then progressively isolated or distanced islands in a straight measure, then this would be perfect. Otherwise, it typically isn't. And then finally, the last pattern is the pattern of species turnover. And here it says that the species are constantly going extinct locally. It's an extirpation on any islands, and then they're replaced by immigrants. So remember that. Extinction locally, replaced by immigrants. And an island, because of its area and its isolation from the larger mainlands, typically has a constant number of species there. So you'll have things go extinct, but immigrants replace them continuously in a turnover fashion. After, say, 1,000 years, 10,000 years, whatever, if all of the geological and oceanographic features tend to be the same, then the area and isolation are such that the turnover is going to be making these islands have vastly different taxa might be there, but the actual number of species will stay relatively the same. Now, MacArthur and Wilson took these two or three patterns and cooked them all together and created their equilibrium theory of island biogeography. So this changed the way we looked at islands, in that they said that islands are unique. They exist in a state of equilibrium as far as how many species are there, and just a few simple factors can explain that. So the three patterns help then explain the number of species there, and you have to incorporate two other things. We mentioned it before. The rate of immigration, how many new species or potentially new species are arriving at an island, and then the rate of extinction or local extinction, how many are going extinct. This is definitely an ecological pattern because it just views these species as static entities. They're just dispersing through time. So it doesn't take into account that there might be evolution or unique evolutionary bursts or adaptive radiations on these islands, although there are people trying to add these models to the overall theory, but it's not quite there yet. So it's an ecological pattern. This is where I'm going to end this particular lecture, and I'm going to start up next time by looking at this important figure. Super important. It's going to be on the next exam, and I'm going to ask several questions from it, and so you're going to have to understand it. So I'm going to go through this step by step, the axes, the units that are counted here, and then this sort of immigration and extinction.